how we can say develop various types of industry, or you can say how we can develop various types of components that we can use in our hybrid drones, and what are the various types of industries that are related to producing the components of hybrid drones and various other things. Okay, so let's start with the session. So in this webinar, we'll be covering about what are hybrid drones, the power source of the hybrid drones, the controller architecture of the drones, and the structure design. That means what is the power source means? Remember, hybrid drones are you can say they're very heavy drones, and they belong to medium and large size category. They belong to medium and large size category. Okay, just 1 second. Okay, so we'll be discussing about the power source of hybrid drones, the controller architecture, and the structural design. So first of all, what are hybrid drones? We can say hybrid aircrafts or drones are unique type of aircraft that combines the hover capability of helicopter with speed and range of aircrafts. You can see in here, there are various images of drones. There is a H-tall image, there is a V-tall image, and there is a hybrid image. That means, you can say H-tall means horizontal takeoff and landing. V-tall means vertical takeoff and landing. We only know, or you can say most of us know about quadcopters. Quadcopters have 4 rotors, and they are generally used for vertical takeoff and landing. Or you can say their flight takeoff process is vertical, and some of the drones we have their flight takeoff process is horizontal. That means you can say they take off horizontally, and our drones or quadcopters they take off vertically. Hybrid drones, they have the capability of both horizontal and vertical takeoff. Your hybrid drones, they have the capability of both horizontal as well as vertical takeoff. They're very large drones. You can see in here. Hello, my voice is breaking. Is there any problem in the voice?
No, sir. Voice is clearly audible.
Okay. So you can see hybrid drones are the type of drones that are capable of both horizontal as well as vertical takeoff. Okay. In hovering mode, hybrid aircraft behave like a helicopter and can vertically take off and land. The transition mode is the flight regime of converting from helicopter to airplane and vice versa. That means in a hybrid drone, we can perform both horizontal and vertical maneuvers. Okay, that means we don't have to use any, you can say, dynamic angles. We have 3 types of angles in a drone. That is not angles, 3 type of rotational maneuver. That is, first is a pitch, then second one is roll, and third one is yaw. You can say if this is the axis system of your drone, this is Z, this is X, and this is Y, then this is your pitch. That means rotation about X axis. Then this is your roll, that is rotation about Y axis, and this is your yaw. Okay, that is rotation about Z axis. So we have 3 angles, roll, pitch, and yaw. But these 3 angles, if we perform any type of maneuver using these 3 angles, there is a certain rotation of the system for which instability may occur in the system, right? Let's say if you have a camera, though cameras, they have gimbal system. Okay, they have gimbal system. But still, if you can perform both horizontal and vertical maneuvers, you don't have to change the orientation of your drone. The drone will be complete, you can say it will be completely vertical. It will be completely straight. Or you can say it will be completely vertical. You won't have to perform any kind of rotation in order to provide any type of motion. Let's say if you want to move forward, so you have to provide a pitch motion. If you want to move sideways, you have to provide a roll motion to your drone. If you want to move upward, you have to provide you can say for moving upward, there is no motion required. Okay, means rotational motion required. So if you perform this type of maneuver and you perform the translations, that means along X, Y, and Z, then obviously there will be a change in the orientation of the drone. And if you are carrying any type of payload on the drone, or you can say if the payload is orientation dependent, then what will happen? There will be a imbalance in the payload, okay, for which you can say nothing will happen, but still you can say the stability of the drone will be very low. Okay. And you can say that the hybrid drones, they're very large drones. They carry engines with them. Engine is there and battery is there. We'll be talking about the power source. They have engines and they have batteries. So you can say providing these motions to a drone you can say it is provided at a compensation of a lot of energy. Okay, because you have to stabilize the drone while it is rotating. Okay. Vertically it is stable. Vertically it is stable because of the thrust forces of the rotors. But after that you have to what? You have to distribute the thrust forces on the rotors in such a way that you can stabilize the drone in an inclined angle. Hence, you have to, you can say it will cost a lot. It costs a lot of energy. Hence, you can say your hybrid drones, you can say there no need to perform any type of orientation, though orientation can be done, but still you can perform various degrees of you can say maneuvering without orienting the drone because they have the capability of both horizontal and vertical motion, okay, without changing the orientation. In forward flight mode, the aircraft is a fixed wing aircraft that offers a wide range of speed and maneuverability. Hybrid drones are mostly used in military application, agriculture, and survey. You can see that in agriculture, you have to carry a lot of payload. Okay, you have to carry, and you can say spilling can also be there. If your drone is rotating a lot, or it is changing its orientation about its axis, or if it is rotating about its axis to perform any kind of maneuver, then spilling can occur in your drone. For which, if you use hybrid drones, then by changing the or by distributing the rotor, you can say the power on the rotors, you can achieve both horizontal and vertical or a combination of horizontal and vertical motion, and you can perform any type of maneuver without orientation. Okay, you can see the image. Generally, the UAV, unmanned aerial vehicle propulsion systems, consists of fuel, hybrid, and electric. Fuel means, you can say, the engine will be driving a system, means there will be an engine, it will be driving the system. It can have ramjet, it can have a turbo. Okay. Fuel, piston, the engine is there to run a generator, and generator will run various electronic components. Or there is a ramjet, ramming. You have to perform ramming operation in order to get the required thrust, or there is a turbo. We'll be discussing about all these things. Then we have hybrid. Hybrid means both engine as well as a battery is used. It has parallel combination, series combination, parallel combination of engine and the battery, series combination of the engine and the battery. And again, we have series parallel and complex combination. Then finally, a fully electric hybrid drone that has power supply, EMS, motors. In motors, we can have PMSM, that is permanent magnet synchronous motor, brushless DC motor, and superconducting motors. So first is pure electric propulsion. In a UAV platform, it is critical part of the mission execution. The generally UAV vehicles consist of the general UAV vehicles consist of energy flight control system, power propulsion system, communication modules, and energy management system. So if it is a pure electric propulsion, then the battery has to drive all these things. It has to drive a control system. It has to drive a power propulsion system. It has to drive a communication module and the energy management system. Okay. In pure electric aircraft, the batteries generally supply energy mainly used to maintain all the UAV systems and loads, while the energy management system controls energy distribution. In order to run all these components, the battery generally uses the energy management system in order to supply energy efficiently to all the loads and the systems. In the electric propulsion system, high energy density and low loss converters are usually required to achieve the system's energy management and motor control. Just 1 second. Okay, because I should be starting one with fuels. Okay, no problem. There is a term. Okay. So first we'll be covering the pure electric propulsion, then we'll go for fuel, then we'll go for hybrid. In yes, high energy density and low loss converters are used. Often unidirectional and bidirectional converters are used in the middle of power supply and DC bus to accomplish the battery charging and discharging control. Generally, what are the low loss converters and what are the unidirectional and bidirectional converters? In our hybrid drone, if it is a pure electric propulsion, then the battery voltage would be nearly 120 volts, 150 volts, or even 200 or 220 volts. A battery. Now, our motors, the motors that we use in our hybrid drone, they don't have that high potential difference, or they don't have that high potential. That means they can't run, or they are not compatible with that much amount of potential. So what we have to do, we have to step down the voltage or potential in order to run our motor and our energy management system as well as the power electronics. So various types of DC to DC converters are used. In an electric vehicle, you know about the DC to DC converters, buck converters and boost converters. Buck converters are used to step down the voltage. Boost converters are used to step up the voltage or boost any current supply. Okay. So in the same way, in pure electric hybrid drones, these buck converters and boost converters are also used. And they are very low loss converters, often unidirectional and bidirectional converters. And why? Why you'll be saying that? Why, sir? In conversion, what is the loss? Obviously, if we are using any transformer for conversion, then obviously there will be magnetic loss, there will be core loss, there will be a whole lot of losses. And if we are using a PSM, okay, or sorry, PWM, pulse width modulator, okay, if we are using a pulse width modulator in order to step down or step up our signal, then it can heat up because of continuous switching. And you can say most of the power is getting, you can say, lost because of heat. So converters that are used in hybrid drones, they have a very low power consumption. UAV often use permanent magnet synchronous motors as a power source device because of their high efficiency, high energy density, high speed, reliability, and ease of control. Permanent magnet synchronous motor. Why we use permanent magnet synchronous motor? It is because since we are using an already magnetized core, we don't have to use additional energy for magnetization. We only have to supply the energy to the stator, okay, or the rotor. We just not, you can say, not energy is not supplied to the rotor. Only in you can say brushed DC motor, the energy is supplied to the rotor. But in all other motors, the energy is supplied to the stator. And the rotor is either it is a you can say coil winding with a soft iron core for or you can say it runs on magnetic induction like induction motor, or we have a permanent magnet, or we can have a switched reluctance motor. But in our drones, generally we use PMSM motors, permanent magnet synchronous motors, since already the rotor is magnetized. Hence, you can say we don't have to use additional energy to magnetize it. And why we call it as a synchronous motor? It is because the rotational frequency matches with the supply frequency, or the rotational frequency is an integral multiple of the supply frequency. If the supply frequency is 50 hertz, okay, if the supply frequency is 50 hertz, then the rotational frequency is a multiple of the supply frequency. That means 50.4 hertz or 50.6 hertz rotational frequency. What is rotational frequency? Cycles per second, RPS, rotations per second or cycles per second. 50 into 10 to the power 6, sorry, into 6 is what? 300 cycles per second or 300 rotations per second. Okay, so it is an integral multiple of the supply frequency. If it is 60 hertz, then you can say it will be, the first one will be 60 multiplied by 4 is 240 hertz, 240 RPS, and 60 multiplied with 6 is 360 hertz or 360 RPS. This is why we call it as a synchronous motor. Now in pure electric propulsion, what is the power flow diagram? This is the power flow diagram for our pure electric converter. This is the power flow diagram for our pure electric converter. There is a source, power source, that is generally a battery. Then we have converters. Then we have DC bus, inverters, motors, and generators. Why do we have to use inverters? Again, generally, we have to use 2-phase or 3-phase motors. We have to use for proper control of the motor. If we want to have extensive control on the motor or rotation of the motor, then the motor a should be a two-phase or three-phase motor. But our power source is only a single phase. Our power source is only a single phase. Hence, we need inverters to convert single phase to three phase. And another thing is when we run a motor, remember the RPM of the motor is controlled by the voltage, supplied voltage. Okay. Or you can say voltage controls the RPM and current controls the torque. Voltage controls the RPM and current controls the torque. But our battery supplies only a fixed potential difference. Yes or no? If we are using a 12-volt battery, then we only have a fixed potential difference of 12 volt. But in a motor, we have to change the voltage to achieve a desired RPM. Yes or no? You have to change the voltage. Current can be changed. We just need a resistor. By changing the resistance of the resistor, we can change the current. So there is no problem of current. Current can be changed. But our potential is constant because we are using a battery and we can't change the potential difference across the terminal of a battery dynamically. For that, we have to perform a lot of things. It can be done easily. Okay. So how to run the motor and or how to change the voltage? For that, again, we use inverters. We have high frequency switchings. And when we take the average of those switchings or time period of those switchings, then we get the required voltage. Okay. For that, we have to study about PWM generators. Okay. I'll not be covering about PWM generators. We can find those things in in our courses or any other area. There are a whole lot of resources to find those things. So PWM generator, pulse width modulator or pulse width modulation generator. What it does, it sends the signal from the battery in pulses, and when we find out the average of those pulses and we multiply it with the duty cycle, then we get the required potential difference across the motor, for which we can control the RPM of the motor also. Then we have finally the gearbox for our reduction, then the propeller. Then all these things are done by the energy management system. After that, we have fuel propulsion. The fuel propulsion system of a UAV generally consists of fuel supply system, engine, mechanical transmission, and propeller. In the system's structure, engine is the core of the fuel propulsion system, playing the role of energy conversion and UAV power supply. Fuel engine can be classified into two categories, piston and turbine based. So in our hybrid drones, generally a piston is used. Remember, when piston is used, either we have UV universal joints to run the propellers, or we have a generator that will again run the motors. Engines suitable for UAVs need to have many characteristics, including long endurance, small volume, high power to weight ratio, robustness, and ease of maintenance. Generally, the size of engine for a hybrid drone is a bit small. Its capacity is some, you can say 50 cc, 60 cc, is the cubic capacity of those engines. Okay, but they have to produce a lot of power from those or with those capacity, and they need to be very robust, and there should be ease of maintenance. So fuel propulsion system, there is a fuel tank, there is an engine, then gearbox. Okay, this is for mechanical transmission of power. That means if we want to rotate our propellers mechanically, okay, so this is our drone. You can say, let's say this is our drone, and if we want to control our drone mechanically, then here we have the engine, then you can say universal joints are connected. Universal joints are connected to rotate it. Okay. Universal joints are connected to rotate it. Okay. But that type of engines or that type of drones are not manufactured now. Okay. They are manufactured, but they are not that widely used because a lot of that much, or you can say those drones weigh a lot. Okay, those drones they weigh a lot. Then we have turbojets, turbofans, then turbopropellers and turbosans. Remember, in here also we use a piston. In turbojets, turbofans, we also use a piston. But the piston generally rotates the turbojet. Okay. The piston generally rotates the turbojet. We have to use a fuel or we have to use a motor. Anything we have to, but we have to use a device to rotate the turbojet. It does not rotate automatically. We need an engine in order to rotate this turbojet. And once it is rotating, you can see in the intake, it will capture the air. Okay, in the intake, it will capture the air. It will compress the air. It will increase the density of the air. Then you can say in that density, fuel is mixed and there is combustion. So when there is combustion, there is an additional thrust. When there is combustion, there is an additional thrust because we have energy. We have a lot of energy. Now we are directing that energy in a particular direction. Because of combustion, a lot of energy is generated and we are directing that energy in a particular direction for which there is lot of thrust. First is there is lot of motion in the system. When there is combustion, you can see there is high amount of motion in the system. Now what we are doing is we are just directing that motion to a particular direction for which we get an increase in thrust. So this is what is the concept of turbojet. There is an engine to rotate the shaft. Then when the shaft rotates, it has turbines, and the turbines capture the air or draw the air, compress the air, and in that compression chamber, generally fuel is mixed and ignited. So there is combustion. When there is combustion, there is lot of energy generation or there is lot of motion in the particles. Then what we do is we just direct that motion in a specified direction for high thrust. Then we have turbofans. We have turbofans. In here, you can say another type of system is used, that is air is again introduced at the end of the nozzle for improved combustion because already the temperature is very high. So when we supply additional air, so additional oxygen is available. So unburnt fuels also starts burning, for which again there is high amount of thrust. Then turbopropeller, where we have a, you can say fan that generally inducts the air to the compressor, then combustion chamber and exhaust. Then turbo shaft. There is a shaft that rotates. Again, the shaft is rotated by an engine. Okay, the shaft is rotated by a engine or a motor. And when the shaft is rotates, again it inducts air or it captures air, compresses the air, mixes fuel with it, then combustion. Okay, there is combustion. And after that, there is direction of, you can say directed combustion. The combustion is directed along a given direction for increased thrust. In our piston engine and rotary engine, generally 220 to 400 HP of power output is there. We reach a RPM of nearly, you can say, not only fan, remember, we not only use fans, turbojets are also used. If you see in the drones, okay, sir, only fans are used. No, small thrusters are also used, generally run by the motors or battery or engine. Okay, small thrusters are also used. Just 1 second, guys. Okay, small thrusters are also used in order to propel the drone. Okay. And same, we can rotate the thrusters and we can achieve both horizontal as well as vertical flights. We can achieve both horizontal as well as vertical flights using fan or using propellers or using thrusters. So piston engine, rotary engine, they have a RPM of nearly 3000 to 7000, 6000 to 12,000. Power to weight ratio is 0.76 to 1.37. Very good weight to power ratio. Rotary engines, piston, as you can see, these are piston engines. Generally used to rotate using mechanical communication, mechanical links or using generators to run the motors. A propulsion system is a system that generally, obviously, as the name indicates, propulsion system is something that propels. Propulsion system means something that propels. Either if you use a fan, the fan creates a pressure difference for which there is motion in the body. If you have engine, again you need a fan or a turbo engine in order to create a pressure difference for motion. Or if it is on the ground, then you have to use a rotating object to create a translation motion. So these are propulsion systems. Speed, the amount of speed that we achieve in our drone is generally 110 to 260 km per hour in our piston engines. Then flight height is generally 2500, you can say, meters to 9700 meters. Endurance time is less than 40, very less endurance. Flight weight is generally less than 1100 kilograms. Okay. This is time endurance in hours, in meters, speed in kilometer per hour, power to weight ratio in kilowatt per hour, kilowatt per kg. Turbojets, generally output is 170 kilonewton. Rotation is, I can say, rotating RPM is very fast. Power to weight ratio is, you can say, 10. Speed, we achieve a speed of nearly 700 to 1100 kilometer per hour. That means the drones, they can fly very fast if we use turbojets. Then flight height is 14,000 meters to 3000 meters. Sorry, 3000 meters to 14,000 meters. Remember, these are unmanned aerial vehicles. There is no personnel driving these vehicles or these drones. And remember, these are utility drones. We not only use the drones in order to, we can say, make them fly. We install different types of sensors or machines on the drone to perform a specific operation. If I want to survey, then I have to install a camera, an infrared sensor, spectrometer, all other things. If I want to use the drone for leak detection or for maintenance, generally not for this type of heavy drones are not used for maintenance, but still for payload carrying. If the drone has to carry a payload to a certain height, to a certain distance, then we can use this type of specifications on the drone. Yes, obviously. There is a lot of possibility. Actually, they are installing ramjets or pulse jet on drones. Okay, they are installing. It is available. Small thrusters are available to run. Then turbo propellers, speed of 350 to 500, turbo start speed of 180 to 300. Then fuel electric hybrid propulsion system. So we have studied about pure electric propulsion system. Then we have studied about only fuel propulsion system. Then we will be studying about a fuel electric propulsion system. Okay. A fuel electric propulsion system. Okay. The development of fuel propulsion system for a UAV is becoming increasingly mature. However, with increasing depletion of petroleum resources and climate problems, the traditional fuel propulsion system can no longer meet energy and environmental protection needs, while the pure electric propulsion systems is still under development. The pure electric propulsion system is still under development. Okay. And the fuel propulsion systems are reaching their end of life. Actually, they will not be reaching their end of life. Generally, the petroleum products or petroleum resources will be replaced with biofuels. There will be engine that will run on biofuels, but still you can't prevent the production of carbon dioxide. little carbon dioxide will be produced, but still there will be no restriction on these drones, because once all our transportation vehicles gets converted to electric vehicle, obviously there will be a large reduction in carbon emission. So we can use biofuels in order to run our drones, or we can use fuel cells, but fuel cells are very heavy. Hence, it is very difficult to install fuel cells on drones. We have to carry hydrogen cylinder, oxygen cylinder, very difficult. But solar as well as biofuel engines can be used. The problem of battery is the energy density. The problem of battery is the energy density. It restricts its further application, resulting in PEP. PEP means pure electric propulsion. PEP means pure electric propulsion system. Not fully meeting the needs of air transportation. People have purposed full electric hybrid propulsion system solution. So a lot of researchers and lot of institutions, means industrial researchers as well as you can say university researchers, they have proposed that we should go for full electric hybrid propulsion system for a better fuel efficiency and meeting the environmental protection needs. Okay. Then fuel electric propulsion architectures. What are the various types of architectures of a fuel electric propulsion of a drone? Parallel hybrid, series parallel hybrid, and complex hybrid are the various types of architectures in a fuel electric propulsion system of a drone. You can see it is a parallel hybrid propulsion. Parallel hybrid means there is a fuel, there is an engine, there is a battery, there is a motor, and both of them are connected to the gearbox. You can see both the engines and the motor, or both the engine output and the motor output is connected to the gearbox. That means there is power, you can say parallel flow of power. There is parallel flow of power between the engine and the motor. We can use various types of, you can say, clutching mechanisms or shifting mechanisms in order to shift the power flow from engine to motor, or to combine the power output of the engine and the motor to get the required output and thrust. Then series hybrid propulsion. In series hybrid propulsion, we have a fuel, then we have engine, then we have generator, and we have a battery, and we have a motor. So there is an engine that runs the generator, and the generator in return runs the motor and recharges the battery. So we can have a either complete engine drive mode, or we can have a battery drive mode, or we can have both engine and battery drive mode. But the powertrain, or you can say the final output of the powertrain, comes from the motor only. The final output of the powertrain comes from the motor and it is connected to the gearbox. Not the final output, but the power. The power of the powertrain comes from the motor only. The motor is run by the generator, powered by the engine. And the motor can also run through the battery, charged by the engine through the generator. Then we have series parallel hybrid. In series parallel hybrid, the architecture is a bit complex. Why? Because you can see the engine is connected to a mechanical coupler, then a generator is connected to a mechanical coupler. Okay. And the mechanical coupler is connected to the gearbox. Again, there is a motor controller and there is a motor connected to the gearbox. And the generator also recharges the battery and runs the motor. So the engine is in series combination with the motor and also in parallel combination with the motor also. The engine is in series combination through this path: engine, generator, power converter. So, what is the direction of connection for the engine? In series, if it is a series drive. Okay. You can see engine to the mechanical coupler, then mechanical coupler to the generator, generator to the power converter to the motor. You can see motor to the gearbox. This is series combination. Parallel, engine, mechanical coupler, then gearbox. parallel combination. So both the engine can be in series and parallel combination with the motor through this series parallel hybrid. Okay. They provide a robust control on the power management, energy management, and also on the maneuverability of the drone. Then complex hybrid. Complex hybrid is similar to series parallel hybrid, but in complex hybrid, generally we use you can say our planetary gearbox. In complex hybrid, we generally use our planetary gearbox. Okay. Okay. Sorry for the disturbance. Okay. So now you can see in the series, the propulsion system is powered by electric motor only. In series, the propulsion is powered by electric motor only. Advantage is simple structure, easy to control and maintain, then low cost. Okay. These are the advantages of a series supply of power. Then disadvantages, high emission, low efficiency, but only has electric motor. Parallel, the propulsion system consists of an engine and an electric motor working together to generate power. High max power, have fuel and electric modes, high reliability, greater performance at high speed. But high emission, low efficiency, and short endurance. Series parallel, integration of series and complex structures which can work in a single or dual mode respectively. High efficiency, high reliability, long endurance. But structure is complex, control is hard, and cost is very high. Then complex, a converter has been added to a series parallel to independently power the motors. Generally, the converter is a planetary gearbox. High efficiency, various operating conditions, better performance. Complex structure, more difficult to control and high cost. Okay, then a simple structure design. Okay, a simple structure design. Okay, architectural structure design of the drone. So generally, when we try to design the architecture of a drone, you can see generally there is a PID controller. There is a PID controller. What is a PID controller? Remember, any controller that we see on any device, it has a PID controller. What is PID? Proportional integral derivative controller. Remember, the controller requires three types of information for proper control: the past information, the present information, and the future information. For a controller, if you want to control an event, then you should know the past values of the event, the present values of the event, and the future values of the event. That means what was going on, what is going on, and what will happen. Only when we can create a very good control system. Because of that, we use PID controller. Because PID controller can know, or you can say can store the information of the past, can work on the current values, and can predict the future values also. There is a proportional controller, P for proportional, I for integral, and D for derivative. Proportional controller works on the current value of the system, or current value of the current value of the system. Integral controller works on the past values of the system, while derivative controller works on the future values of the system. Okay. Proportional controller works on the current value of the system. Integral controller works on the past values of the system, and derivative controller works on the, or it predicts the future values of the system. Okay. See, prediction is not done for 1 hour or 1 month. Prediction is just done for few seconds. Okay. What will be the state of the drone in next 3 seconds or 4 seconds? If we are performing or we are under a certain state, when the drone is flying, if it is under a certain state, so what will be the drone position in next 3 seconds or 4 seconds? That much is enough for the controller to stabilize the system. Okay. Let's say if the drone is rotating. Okay. If the drone is rotating, the PID controller finds out that in 3 seconds or in 4 seconds, in next 3 or 4 seconds, the drone will reach a position where it will become unstable. So before reaching that position, the PID or the controller starts sending the signal to stabilize the drone. Okay. It starts sending the signal to stabilize the drone. Better the design of the PID controller, better the stability of the drone. That means it will always use the past values, what was the position of the drone, what is the position of the drone, and what will be the position of the drone. What was the position of the drone before 3 to 4 seconds or 5 seconds? What is the current position of the drone? What will be the position of the drone in next 5 seconds? So if we have information of these things, then we can better control the drone. Okay. If the drone is going for any high roll rate, then send the signal in such a way to reduce the roll rate. So that is what the use of PID controller. All the controllers, they have PID controller. Now we have, you can say, machine learning controllers, machine learned, or you can say not machine learning controllers. The controllers work on the principle of machine learning. They can also work very well, just like a PID controller, because they have a memory to store the past values. Then they have a processing unit to work on the present values, and they can predict the future values using regression. Okay. They have memory. When we create a net for machine learning, then the nets have weights. The weights carry the memory, and also the weights can perform regression operation for prediction of future values, and they can work on the current value also. Okay. It means a single network can control all these things. But still, PID controllers are very robust for stability of the drone. But when you want to make your drone very alive. Okay, remember, PID controllers are very strict. Okay, they're very strict. You can just relax the PID controller for very natural motion. If the PID controllers are very strict, or they are very, you can say, strict means, you can say the relaxation factor of the PID controller is very low. Then the drone will have very, you can say, strict motions. Okay. That means it will have very fast and strict motions. But if the PID controller is relaxed, then it can have some natural motions. Okay. Naturally, how it will fly, it will be flying like that. Okay. For, you can see, if you have a relaxed value of the PID controllers. Now, if you have a, you can say, model based on a machine learning, then you can have very natural, very good and very natural controller, and it can have much more robustness than that of a PID controller. Because PID controller works on hard mathematics, but your machine learning, or you can say machine learning model, works directly on the learning. That means it is continuous. PID controller can't improve on a certain situation. Okay. It will only work on stability. It can't improve itself. The PID controller can't improve itself with time. In order to improve the PID controller, we have to again remove the old data and provide the new data. And that also, it cannot go for dynamic improvement. Once the values are set, it will work like that one. So if the environment changes, let's say you are flying your drone in a environment where the wind is not that, or you can say there is no wind, or there is no gust. But when the drone enters an area where there is a lot of wind gust, then the drone may reach instability. Okay. There will be a lot of instability. Okay. So you can see we have machine learning models for proper stability, and you can say for robustness of the drone. The drone controller consists of a bunch of different PID controllers. The PID controllers are responsible for stability, angle correction, for manual control, displacement. PID controllers for navigation. The drone controller has a complex design in order to deal with different types of PID controllers. You can see this is a simple MATLAB architecture that we will be designing in our long term, or you can say 1 month or 1 month drone sessions. Okay, we will design this full drone controller in MATLAB. Okay, that is now out of the scope of this session. Okay, so generally in long-term sessions we cover the whole controller design of a drone in MATLAB. And we also design the PID controllers. You can see in here there are 3 PID controllers for roll. You can see this is for throttle, roll, pitch, and yaw. There is no yaw requirement, hence there is no PID controller for yaw. Stabilized PID controller. It is responsible for maintaining the drone from a given position from the manual controller. It consists of 3 PID controllers for different direction: roll, yaw, and pitch. The input of the PID controller is the manual input rate for the different directions as the input of the angular controller. The angular controller is fed from the pilot joystick by the target position. That means the user provides the required input and the PID controller provides the required output in order to maintain stability. See, remember, you can say the user required is also modulated. The user requirement is also modulated for proper stability. That means user does not have the full control. Okay, it has the full control, but still some of its responses are managed properly. That means if you move the joystick slowly, then the drone will move forward very slowly. But if you move the joystick very fast, will the drone go at a light speed or it will move at the speed of light? No. So that is the stability that the controller has to maintain. If you move the joystick slightly towards the left, then the drone will also move slightly towards the left. But if you move the joystick very fast, then will the drone move very fast? No, it will move slowly, or it will not move slowly, it will move in such a way to maintain the stability of the drone. Okay. So PID controller design, the position PID controller consists of 2 cascade controllers, one proportional while the other one is a PID controller. The controller is fed by desired position and the actual position of the drone. The first is proportional controller, which uses the error in the position and it converts to desired speed. So what I have shown in here is a PID controller. Okay, I'll be reading these things out, then I'll be saying you what is this, what is the working of PID controller. The desired speed is the input for the second PID controller, which is converted to its desired acceleration. So this is what I'm saying, that if you provide a certain input to the PID controller, the PID controller acts on the input to provide the required output. Just like if you just move the joystick very fast, the drone will not be moving at that speed. The PID controller will manage the input, or it will handle the input in such a way that the stability of the drone can be maintained. The resulting desired acceleration become a lean angle, which is then passed to the stability PID controller to regulate the angles. This is the PID controller. You can see this. This is the, you can say, mathematical architecture of a PID controller. There is a KP1. KP1 is the proportional constant. D by dt is the derivative controller. Then it is fed to the P proportional. There is a proportional controller in here. Generally KP. Okay, or KE is the error. Integration of KIE. That means this is the integration constant and E is the error. And derivative controller again KD dE by dt. Derivative controller on the error. So proportional controller directly working on the error. Actually, error is the difference between the input signal and the output signal. You can see the sensors, they are providing the feedback and there is an input. So there is an error between the input signal and the output signal. That is the error. The PID controller works on the error, because error generally increases or decreases. If the error increases, the stability is decreasing. If the error is decreasing, then the stability is increasing. Okay. So your PID controller works on the error. It directly works on the error using proportional constant. It works on the past values of the error by using integration constant. It works on the future values of the error, or it predicts the future values of the error using the derivative constant. This is a simple controller. And you can see this is the PID controller with KP proportional constant, KI derivative constant, KD integration constant. And this S is actually a complex number because we have to perform Laplace transform. Remember, when we perform any planned design, the design is generally converted to a solvable model using Laplace transform. Your S is sigma plus Ij, or sigma plus I omega. Okay. Sigma is the real value, I omega is the complex value of this S. Okay. S is equal to sigma plus I omega. And this is your plant. Plant is the drone, this is the controller. Okay. And this is the sensor. We'll also be covering about this plant and sensor models in our full term courses. Then this is a stabilizing graph of your PID controller. You can see how the PID controller is oscillating and also getting stabilized with time. Then PID tuning. Generally, the PID tuning is available directly in the system. Okay, it is available directly in the system. You can see these are the tuning graphs of PID. Okay. Then communication architecture. Remember, in our drone, generally we have various types of processors, and the processors you can see we generally develop the PID controllers in MATLAB. You can see this is a PID controller developed in MATLAB, and we convert this or we upload this PID controller to a hardware, and this is the hardware architecture of the controller. There is no directly PID controller. The processor, you can say PID controller is actually a mathematical architecture. That architecture is uploaded to the flash memory, and the processor calculates the outputs based on those architectures. Okay. There are different types of communication protocols to transfer the data between the different modules. The flight controller captures the data of the position from the IMU using SPI protocol. Also, the motor output transfer by UART protocol to the FPGA, which is fed to the motor by PWM input. You can say, talking about PWM, that is pulse width generator. FPGA is flight controller. Okay, it is a type of flight controller. Okay, so we have reached the end of this session. So let us again recap what we have covered in this drone session. So what is a hybrid drone? What are the various power sources of a hybrid drone and the propulsion architecture of the hybrid drone? Pure electric propulsion, fuel propulsion, then various types of thrust increasing methods, then fuel electric propulsion, parallel series, we can say series parallel, and also complex hybrid propulsions. Then architecture design, what are PID controllers? Okay, so complete architecture design, then how to attain the stability of the PID controller, then the stabilized PID controllers, the design of PID controllers, how we can design the PID controllers. Remember, I have only provided you the theory of PID controller. Okay, not the complete theory, only the steps of PID controller, but we have to use mathematics, hard mathematics, not very difficult, actually very easy mathematics. Only small differential equations. We have to work on small differential equations to create the whole system for drone. Okay, very easy. Not that difficult. You can see in here the PID controller is very easy. Okay, this is the whole PID controller. Okay, nothing else. Only you can see that there are certain types of the electronics is very difficult to, you can say very hard to see, but the electronics is also easy. You just have to step down, step up the voltage, modulate the current, do some switchings, electronics is done. Basics, I'm saying on the basics of electronics is to control the voltage, control the current, and perform certain type of switching. That's all. And then you can these are the basics. Then on those things you can create a very complex system or any type of complex system you want. Okay, then PID tuning, graphs, and finally the communication architecture. So